Okay, let's look at how we calculate weak acid calculation. So at this point, you should know how to write the equilibrium expression, as in that when we have equations such as this, like how water dissociates into your hydronium ion or your proton. So I'll just write both of these in hydroxide ions. You should be able to know that the equilibrium constant, or the Kw, is the H plus or H3O plus times OH minus, and that's what your equilibrium expression. We don't include the H2O because it is in a liquid state, so that we can't really determine the concentration of that because it's nothing dissolved in there, so that the liquid state is going to be neglected. That's why you have the concentration of just these two, your hydronium ion or your proton, in aqueous state, and also hydroxide. However, though, when we look at weak acids or weak bases, that's going to change a little bit. So we're going to see how that's going to be affected. Also, at this point, you should know that strong acids and bases, in terms of dissociation, so that means that both strong acids and bases will completely dissociate into its ions, and which makes your stoichiometry molar ratios a lot easier, because whatever you start off with in the reactants, that's what you're going to end up with in your products, because it's a complete dissociation. And after you have calculated your proton concentration or hydronium ion concentration or hydroxide, you should know how to calculate the pH from each of those ones, and also know how to calculate these from Kw of a strong acid or base. So this is where we're at now. And when we talk about Kw, that's your ionization constant for water, right? So this is just how water dissociates. But there's also one ionization constant for acid, that's why it's called Ka, and there's also one for base, that's why it's called Kb. So if we were to look at the Kb for 1 second, if we were to look at the weak base of ammonia, so you can see that this is ammonia in aqueous solution. And then you have your water, so this is dissolving into water, and then you get ammonium in aqueous and hydroxide in aqueous. I would say that this ammonia should have been in gas form, because ammonia is usually found in a gaseous state. But regardless, this is going to be included in your equilibrium expression. That means that whenever you write your equilibrium expression, you're just really looking at the ratio of your products divided by your reactants, right? That's really what it is. That's what your K represents. So when we look at that, if you look at your products, you have the concentration of ammonium, so that's why we have square brackets, times the concentration of your hydroxide, and both of these are going to be divided by the reactants. So we only include your ammonia in this case because it's aqueous. We don't include the water because it's the liquid state. And you also don't include solid state as well. So this is your dissociation constant, ionization constant for the base. So you're going to be given a table of Kas and Kbs. That means that those values are going to tell you what's the ratio between the products of the ions dissociated with the reactants. So sometimes you might get a number that's like 2.3 times 10 to the negative 6, for example. That means that this constant number, how do we get this number to be so small? Well, in order to get a really small number, your numerators, your concentration of your ions dissociated, must be really small. That's why it's called a weak acid or weak base. If we were to look for a strong acid or strong base, Ka or Kb value, the number will be quite big because you have 100% dissociated. So whatever you start off with your concentration, you're going to get as your product. Okay, so that's what a weak acid is. So let's look at a couple calculations here. The only difference between weak acid and base calculation is that there is no complete dissociation. We talked about this quite a bit. Let's look at this first example. Calculate the hydrogen ion concentration in a 0.1 molar acetic acid solution. This is your formula. And then the Ka for acetic acid, which is a weak acid, is this. You notice that this is a really small number. So the first thing you want to do is let's write the dissociation equation. So I'm going to start off with my acetic acid. So this is HC2H3O2. And this is going to, let's just say that this dissociate. We won't even need to add the water here. Let's just dissociate this right off. And you can see that we have your H attached to this ion. So this is going to dissociate into your H+. That's your hydrogen ion concentration. And what you're going to have left is the remainder part of that. So you're going to have C2H3O2. And because you lost a positive charge, this is going to be a negative ion. So the next part is this balance. It looks like it's balanced because it's a 1:1:1 ratio, so that's good. Let's write in what we're given. So we have a 0.1 molar. So in a strong acid calculation question, you excuse me, you would have just put this amount into here and then also into here because it's a 1:1. However, in a weak acid solution, it does not dissociate completely. So this 0.1 molar will not dissociate 0.1 molar of hydrogen ion. So you cannot make that assumption. So the next part is you are going to write the Ka equilibrium expression. So remember, we're going to include the products. So these ones are all dissociated, so they should all have AQs. And we're going to put H+ concentration times my other product, which is C2H3O2 minus. And this is going to be divided by my H C2H3O2 because this is also aqueous as well, because this is your weak acid was dissociated into something. So here's the thing. What do we know out of my equation? We are given this Ka value, right? The Ka value is at the top right here, 1.8 times 10 to the negative 5. So I'm going to put that and complete this equation. Do I know the concentrations right now? I don't, because those are my weak acid dissociations. That's what I'm trying to find. And then, do I know the concentration of my acetic acid? Yeah, I do. This is your 0.1 molar. So this is what I have so far, 0.1 molar. So then what's the next step here? I'm just going to move this next question down a little bit. What's my next step here is that, well, since we don't know what these ones are, let's use algebra, right? Let's use algebra for each of those. So instead of keeping these into H+ and C2H3O2 negative, we're going to make them into X's. And because they're 1:1 ratio, this and this are going to be the same thing. So we can put an X for each of those ones. And then all the other ones will remain the same with numbers. So I'm going to put 1.8 times 10 to the negative 5. So then this is just like a typical algebraic solve for the unknown calculation. So cross multiply this. I'm just going to bring up my calculator. So first thing, 1.8 to the negative 5 times 0.1. It gives me an answer of 1.8 times 10 to the negative 6. Now x and x is going to be multiplied together to get x squared. And to solve for x, I'm going to take the square root for both sides. So I'm going to take the square root of the answer I just got. So then my answer is 1.34. This should be a 1 here. 1.34 times 10 to the negative 3 is equal to x. So then you have to go back, and what does x represent? Well, x can represent the hydrogen ion concentration, or this C2H3O2 negative concentration as well. Since we don't care about this one, we're just going to say that the X is my hydrogen ion, which is my answer of 1.34 times 10 to the negative 3 molar. So that's how you solve for a weak acid calculation, throwing in an unknown X into your equation. So let's look at one that is about a weak base. So here's the question. You might want to pause the video and see if you can do this on your own. The question is, calculate the hydroxide ion concentration, so this is OH negative, in a 0.025 solution of aniline, which has this formula C6H5NH2. It says it's a weak base, so you can see that this is really similar to the last question, right? So let's write out my dissociation equation here. So I have my aniline. This is going to be dissolved, so I'm going to put water in here. Remember, this is a weak base, so base is an acceptor, so it's going to accept the proton. And where is that hydrogen ion from? It's going to be from the water. So this H is going to be donated to my C6H5NH3 now. And because I have acquired a positive charge, this is going to be my positive. And then since this water lost in hydrogen, so this is going to be my OH. negative because I lost a negative charge. All these ones will be your aqueous except for water, because water is your concentrated pure water. So then let's write your Kb here. So my Kb would be my products, so my concentration of these two ions plus multiply to each other. So these are my products divided by what I started off with. So C6H5NH2. So then let's put some numbers in here. Do I know what my Kb value is? Yeah, so let's go back up here. My Kb value is up here. So 4.3 times 10 to the negative 10. So I'm going to write here 4.3 times 10 to the negative 10. And then let's write my concentrations here. So I start off with 0.025 molar of this aniline right here. I cannot do a complete dissociation because it's a weak base. So I'm just going to write this concentration for my reactants, which is down in the denominator. So this is going to be 0.025. What I have at the top are going to be my unknowns, so I'm going to use the letter X just to represent their X's, and solve for the X just similar to the previous example. So 4.3 power to the negative 10 times 0.025. I got 1.075 times 10 to the negative 11 is equal to X squared. I multiply these two. Take the square root of X squared on both sides to get just X, and my final answer is 3.28 times 10 to the negative 6 is equal to X. And again, what does this X represent? It represents the OH and also this positive ion that's left from the aniline. And don't forget your units. This is concentration, so they all have to have molars. So that's your weak acid or weak base calculation without using the quadratic formula. But the key thing here for you to know is that in a weak base, there's no complete dissociation. So you cannot make the assumption using stoichiometry of how they are 100% dissociated. You have to throw in an unknown or an algebraic term such as X to solve for that. So hopefully that video or this video has helped you. Thanks for watching.